mapping outflows with magnesium-2 emission.
Okay, thanks so much, everyone. I'm a postdoc in the Intergalactic Interstellar Medium Program of Studies, right across the street. And I'm delighted to talk to you about some work I've been involved in fairly recently. These are some exciting new KCWI observations, so I'll introduce our program to you, show some preliminary results, as well as chart the path forward. Okay, so I should also mention my collaborators who are key, Kate Rubin, Allison Coyle, and Xavier Burchett. Okay, so I don't need to convince this crowd, but outflows, or more generally feedback, are absolutely essential to reproducing the properties of the global populations of galaxies. These are not included, these are not limited to, but including stellar mass function, the evolution of the star formation rate density across cosmic time, as well as the enrichment of heavy elements into the intergalactic and circumgalactic medium. Furthermore, observers for more than a decade have been discovering and characterizing absorption, these outflows through absorption, and this is an example here of sort of how this works. So using so-called down-the-barrel spectroscopy, where we use a galaxy as a background source itself, and then observing in absorption the outflowing gas as a blue shifted profile. So this is just showing the systemic profile of a galaxy here in red, and these are just different panels. These are spectra shifted to the rest frame of the magnesium-2 2802 line, and we can see the blue shifted component comprising the bluer end of the profile here. We can then go back to correlate, for example, the relative systemic velocity of these blue shifted components to the intrinsic galaxy properties themselves, such as seen here versus stellar mass, and across a wider range of star formation activity, more extreme objects as a function of absolute galaxy magnitude. Furthermore, in some instances, we can observe outflows in emission where we get a little bit more information, or I should say different information, than we get through these down-the-barrel spectroscopic observations. Here, in this spectacular example, we are able to see this super bubble blown in the circumnuclear starburst galaxy. And so here we get information about the morphology as well as the extent of the outflow, but the velocity information is a little harder to come by. There is another way to go about observing galactic winds, and in particular outflows. And this means is resonance scattering. So we have a continuum source, such as a galaxy's starlight, and surrounding this continuum source we have an expanding wind. In this case, this is just shown here in the circle. This is intended to be expanding away from the continuum source. Photons from the continuum source are absorbed and re-emitted. Those from the redshifted backside relative to the observer are able to pass through the foreground material, whereas we have blue shifted absorption in, for example, magnesium-2 and iron-2, as well as iron-2 is particularly convenient because we have a fine structure transition that will show emission both blue shifted and red shifted. And this just comes about, as I mentioned, the energy levels here, both magnesium-2 and iron-2. These are convenient because in the UV we have resonance transitions, and we can actually approach these from the ground at observe these from the ground at relatively low redshifts. So the resulting line profiles that come about in such a resonantly scattered wind look like this. We have the characteristic P Cygni profile shown here, magnesium-2 and iron-2, and then just broken down to individual transitions where the velocity has been shifted to the systemic velocity of the galaxy. So we can see the blue shifted absorption signal and then the red shifted emission signal for magnesium-2 and iron-2, whereas for the fine structure iron-2 transition, we have both blue shifted and red shifted emission. Okay, so we are intending to leverage this technique to survey galaxies and map their outflows across a wide range of star formation properties and masses. So to start out, we use this candidate object discovered through the survey efforts of Kate Rubin and collaborators, where we can see this merging system here. This galaxy system is actually a much higher redshift than the other galaxy you see here, hence they are marked B and F for background and foreground respectively. So what they found here was using LRIS slit spectra, one angled here and one angled here. They were able to observe, this is just a two-dimensional spectrum, and you can see the absorption here from magnesium-2. In addition, the emission of magnesium-2 that's potentially extended. And furthermore, subtracting the continuum, you can see that indeed the emission is extended. So this is a good candidate for the type of work that we want to leverage with KCWI to get both the velocity information and the morphological information and extent of this outflow. Okay, so this is an HST false color image showing just these two galaxies. I'll now superimpose the KCWI footprint. We're using the M slicer here. This is 20 arc seconds by 16 arc seconds. The slicers will go this way, so we're sampling 0.7 arc seconds going this direction, and then 0.3 arc seconds going this direction. So this is intended to be oriented so that we have the minor axis of this galaxy here. This is sort of a twofer type of observation because we not only get the information about the background object, where we'll be able to map the outflows, but also spatially resolve the foreground magnesium-2 absorption in this galaxy. So they're conveniently located in redshift space and in a spatial configuration to allow us to do that. Okay, so I'll be concentrating on the background galaxy in this talk, and I'll just now show you our KCWI data. So I've now convolved the KCWI cube with the filter response function for the ACS F435W filter. And see the approximate locations of these two galaxies here. The background galaxy marked, see the brighter source here, and the foreground galaxy sort of blended and unresolved off to the side. So let's now look in the spectral dimension. So this is just the same image. I'll now extract, co-add a spectrum of this region here, and we can see the characteristic P-Cygni profile that we expected. That's great. Let's now shift to the systemic velocity of this background galaxy, about redshift 0.7, and sure enough, we can see that we do have this red-shifted emission, blue-shifted absorption. Okay, so now to do some analysis with just these pseudo-narrowband filters, I'll now concentrate on a region into the spectral dimension right around the 2796 peak. And so that's here. You can see the result of that co-addition. I'll now fit a continuum, subtract a continuum, and this is from every spaxel in this image. So this leaves us with this. This is the narrowband around the line with the continuum subtracted. So I'll just point out two things here. The foreground galaxy is gone, and we have this excess emission that is in above and below along the minor axis where the previous background galaxy was. So just A-B these here for a second. And then I'll put the spatial scale here. This is about 30 kiloparsecs all the way across, so about 15 kiloparsecs on either side. I'm now going to exaggerate the vertical dimension here and take these KCWI pixels, which are not square, and make them square. So that's what we get here. I've marked the spatial scale along the vertical and horizontal axes. And now I'm going to extract spectra in bins corresponding to these squares. I'll now show them in the panels here. And what we can see clearly is in the middle regions, in the central regions of the galaxy, we have this strong absorption in addition to the redshifted emission. And then going off the galaxy, even on 10, 15 kiloparsec scales on either side, we have signatures of the magnesium-2 emission. Okay, so to leverage this even further, we are currently in the process of employing a nice radiative transfer code developed by Xavier Pchaska, Kate Rubin, and Daniel Kaysen. And this will simultaneously simulate the spatial dimension as well as the spectral dimension for winds of various properties given various geometries, density profiles, and velocity profiles. And so one consequence of varying these parameters is seen here. So assuming a wind velocity and an opening angle, in addition to some continuum source embedded in this wind, you can see that in the magnesium-2 spectral profile, we get very different results depending on the opening angle of the wind. And so these are just what you would see spatially, extracting narrowband images as I have done in the previous exercise. This is extracted around blue shifted by 250 kilometers per second, 100 kilometers per second, right on the systemic of the galaxy, and then the redshifted emission. So you can see the various differences here in addition to those in the spectral dimension. So we've been running some of these models, varying the parameters. So this is a 45-degree opening angle. We can see sort of at the native resolution of the radiative transfer code what these would look like in the various, over the full velocity range, in addition to these narrow band slices. So this is a 45-degree opening angle, a much wider opening angle. I'll now smooth these to 1 arcsecond seeing. This is something more like we might observe with KCWI. So we can see very strong differences here among these various models. I'll now put up our KCWI image. So as I said, this is a work in progress, but we can start to see that we are approaching the morphology of what we were observing in the KCWI data with this radiative transfer modeling. So this is very promising. We're now not stopping with one galaxy, but actually proceeding to develop a sample through a survey of 15 galaxies. These are star-forming galaxies across a range of star formation rate and stellar mass. You can see our candidate sample, the sample of candidates here. These are taken from the survey by Kate Rubin et al. And our survey targets, as you see in the pink diamonds and orange diamonds, span a range of star formation rate and stellar mass. These were selected in addition to not only a variety of properties, but also based on their profile. So these are just HST images of the targets, and then the LRIS spectra of these particular targets. The equivalent width ratios of the magnesium-2 profiles suggest that these are characteristic of these resonantly scattering winds. So stay tuned for these data. Observations will begin in January. Also advertised some work related to this project being led by a graduate student. He'll be starting as a graduate student at UCSD in the fall. This is Ryan Rickards-Vaught, and he has led an effort at the VLT doing narrowband imaging of a set of 5 galaxies as a pilot program, placing upper limits on both the absorption and emission of magnesium-2. And you can see some of the results here. So these are our KCWI detections that I was just showing you. And then this is surface brightness as a function of star formation rate. So we were obviously starting with a highly star-forming galaxy. He has surveyed some galaxies at a little bit lower star formation rate. And you can see some pretty sensitive limits he's been able to place there. Okay, so with that, I will go ahead and conclude. I'm happy to say we've detected extended magnesium-2 emission around a star-forming galaxy, and this is on scales of about 20 kiloparsecs on the side. The morphology is consistent with a biconical outflow. Stay tuned for more precise measurements and characterization of the wind, and stay tuned for our ongoing survey of a sample of these galaxies to map these galactic scale outflows. Thank you very much.
So I'm dying to know constraints on the outflow velocity and mass flux rate of the magnesium-2 as a function of distance away from the galaxy. What can you give me?
Not a lot at the moment. Stay tuned.
I'm trying to connect the shape, the morphology of the flow to the morphology of the galaxy. Can you help me with that?
Yeah, so I can show you offline, but essentially I've subtracted the morphology of the galaxy. It's relatively edge-on. And so
The
it
flows
would
are
be-
coming out either side.
Yeah, yeah, along the minor axis.
I just couldn't remember.
Yeah, right.
No more questions? Let's thank the speaker again.